Hey, good afternoon, everyone. I'm Giorgio Veronesi. I'm president of the European Federation of Chemical Engineering, EFCE. I've been in the board of EFCE in various positions for 8 years, and currently I'm in my second term as president. I'm a chemical engineer by training, graduated in Padua, Italy, and I've been spending the whole of my career in the engineering construction business, involved in many projects, mainly abroad, with several assignments overseas. I'm very happy today to be in charge of the introduction of this webinar titled Electro-based Processing Technologies for High Quality and Sustainable Foods, and I'm looking forward to participating to it. Let me say something about this webinar series. EFCE is organizing a series of virtual talks on significant topics. We started, now we are in the 5th year of this initiative, which started in 2020 to keep together the community during the COVID pandemic. The success of the previous years convinced the management of EFCE to transform the Spotlight Talk in a regular feature of our program. 10 of our working parties and sections, thermodynamics, membrane, education, static electricity, drying, fluid separation, loss prevention, crystallization, process intensification, chemical reaction engineering, and food, have been delivering over 2 weeks short sessions of 3 or 4 talks focused on specific topics by leading industrial and academic experts. And today, we conclude the spring series with this webinar on the important subject of food. Just a few words about EFCE. EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, representing more than 100,000 of them in Europe. EFCE working parties and sections cover all major aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of EFCE activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. Before concluding, I would like to thank all the people who work hard inside the working parties, the sections, and the EFCE in general for this initiative to happen and to be successful. And in particular, many thanks to EFCE Martin Pou in Toulouse, who is here, who did most of the conceptual setting up and practical activities from the very beginning to the end. So I thank you for your attention and wish all the speakers and the attendees a fruitful and successful webinar. And I would then give back the word to the co-chair of the Food Working Party, Henry Jäger, to start the works. Henry, please go ahead.
Thank you very much, Giorgio, for the introduction. And also from my side, very good afternoon. And it's a pleasure to welcome all of you to today's webinar. This webinar is organized by the section on food, and this section is chaired by Dr. Volker Heinz, who is also the head of the German Institute of Food Technologies. He is not present today, but who is present are the 2 co-chairs of this section. This is Kemal Aganovic, also from the German Institute of Food Technologies, and myself from the University of Natural Resources and Life Sciences in Vienna. And a few words about the section on food. Our key challenge and key task is to translate the basic engineering and chemical engineering into the area of food science, food technology, and food process engineering. And this, of course, is a networking activity, and we need all the different disciplines involved in this multidisciplinary aspect of food processing, which does not only involve engineering, but also involves a lot of material science, and the knowledge about food ingredients and process product interactions. And I think we will hear quite some points on this also today during the talks, although they are meant to introduce some of the technologies relevant for food processing. What are the activities of the section on food? Basically, as we are all here together, organizing networking events such like the webinars, seminars in order to bring together the different areas of expertise, But also a very strong activity is our annual PhD workshop, which is an attempt to bring together all the PhD students in their final stage of their PhD studies from all over Europe. And each year they gather in a different place. They present their work, and out of around 20 presentations, the 3 best presentations are awarded with the Food Engineering Award. And this also involves industrial partners. So we have quite a good set of sponsors from the area of equipment manufacturing, like Alfa Laval, which is quite relevant in the food processing scheme, but also food manufacturers, like some of the global players, Nestlé, Bühler, and so on. And this event always receives a very good feedback for 2 reasons. First of all, of course, we are strengthening the next generation of food technologies, food process engineers. And second of all, we are bringing together the key research facilities from where the students are nominated. And these are very fruitful 2 days of exchange and also looking into the newest research done in the field. Well, this is basically the idea or our aim within the section of food. And today, I think the webinar gives a good example of what we are doing, what we are trying to bring together. And with this, I will hand over to Kemal, who will say some words on the webinar, on today's idea speakers. And then we will dive into sharing the first presentations. Yeah, Kemal, it's yours.
Thank you, Henry. Thank you also, Giorgio, for nice words and nice introduction of the EFCE in general, but also our activities of EFCE section food. Also very warm welcome from my side to our webinar. I'm really happy to see a large audience, large number of people interested in the topics we selected for today's webinar. And if we look a little bit back, then we can state with a high certainty that for decades the researchers have looked and explored the different ways and technologies based on electric energy and how to implement into the food production. And previously, mostly the focus was, okay, can we improve the food quality or improve the food safety by using these aspects? Nowadays, these topics are more or less the same. Can we get better food? Can we get improved food quality? But in particular, also, if we take a look at fluctuating energy prices or increasing energy prices in terms of, in particular, of fossil fuels, then there is good justification and good need into looking into how to apply electrical energy to a food, in particular when we think that this can be obtained through renewable sources like the wind or solar. Using relatively new technologies, I always like to say relatively new because some are longer on the market than the other. We will hear about them today, how the users, we can call them pioneers and users of these technologies, can not only obtain the food with improved quality, but they will also presenters will talk about how they can save energy, even improve their footprint in terms of sustainability, as well as create some new food structures and new food products. So today we try to gather really distinguished speakers, also from academia and from the industry, free to say experts in their fields to present us latest advancement and their potential applications, but hopefully also show us the other side, namely challenges and any opportunities that are related to that. Just a little bit of formal information. The talks will be 15 minutes. We will, of course, allow you to ask some questions. However, we will have 5 minutes for the questions, so this time will be rather limited. We encourage you, though, to actively participate and write down these questions in the Q&A section foreseen in the Zoom application for that field. on regardless on which topic, be it the practical implications, markets, or challenges of the technologies. And depending on the number of questions, as I said, we are limited to only few, but we are willing to collect the questions. And if you leave your contact data, we'll be happy to provide you with answers after the webinar. So, with having that said, we hope that today's shared insights will help you also in striving and inspiring innovation, but also further collaboration with us and in general work and working practices in the area of food production. So, having said that, once again, warmest welcome to the audience and in particular also our speakers. And I would like to hand the word again to Henry, who will moderate the first session.
Yeah, thank you, Kemal. And now it's time already to dive a bit deeper into the technologies. And the first half of the session will basically deal with electric field applications. First presentation more on the non-thermal applications, and then Felix will go more on the thermal applications. And for the first presentation, it's my pleasure to welcome Claudia Siemer. She is also, as the initial speaker, Stefan Töpfel from Elea, a company who basically is working on pulse electric fields since quite a while and was more or less the first ones turning this technology really into industrial use and into robust industrial systems. Besides that, also Claudia is doing quite a lot of research on this area. And since her PhD, more or less, she is in the topic of pulse electric field applications. So it's not only the industrial application and implementation, but also some of the research questions she will probably address in her talk. So Claudia, thank you for accepting our invitation, and we are looking forward to your presentation.
All right. Yeah, thank you very much for the nice introduction. And also from my side, a warm welcome to the audience. And it's a pleasure for me to show you some the nice technology about PAF. I will start now sharing my screen. We checked it in advance. Everything works, and I hope it works. It still works. It seems like it works. Okay. Yeah. I will give you now a little bit a talk about the pulse electric field technology for improving food quality, structure, and increasing process efficiency. To begin with, I would like to give you a short introduction about PAF mechanism. How is it working? What is it all about? So PAF stands for pulse electric field, and the mechanism behind is called electroporation. So by electroporation, pores are formed in the cell membrane, as you can see it here on the slide. And this is working for microorganisms and also for plant cells, as you can see here on the top. How's it working? So if you imagine if the cell is exposed to an electric field, the ions here inside the cells start to move and they collect at the membrane. The membrane here is considered as an isolator, and that's why they are collecting here at the membrane. And the pressure, putting on a pressure on this membrane. At a certain point, this membrane cannot withstand this pressure and it breaks up, and this pore is formed into the membrane. And this is allowing different applications, starting from inactivating bacteria, but also here opening up plant cells to modify the structure. So basically, PAF has different applications, which you can see here on this slide. So we start with French fries, snacks and chips, drying, wine, biotechnology, beverages, vegetable and olive oil. As the time here within this time frame is a little bit limited, I will just focus on a few application areas here. If you're especially interested in one application field, please just let me a note and we can arrange a talk later on. So first I will start with the effect on potato and vegetable processing. So as I explained earlier, PAF is opening up the structures, opening up the cells. And by this, the structure is very soft and it's very easy to cut these type of products. You can see it here on these surface pictures. So we detected the surface of French fries, as you can see it here. And on the left side, you can see the untreated picture, and you can see a lot of hills. Basically, this shows that the structure or the surface is not even. Basically, a lot of cells are ruptured, which means also a lot of cell content is leaking out. Here in this type of products, especially the starch is important. And here with the untreated one, a lot of starch is leaking out, which is in the end yield a loss. When using PAF, you have a very even surface, as you can see it in the picture. And by this, you also retain a lot of starch in the cell, which means the industrial users have a higher yield impact. By having an easier cutting, you can also produce different cuts, like here, purple sweet potato or sweet potato. You can see here that you have very sharp edges here, and it's possible to create even new shapes. So the product is so flexible that you can easily also make a nut in a fry out of sweet potato or out of this potato cell. Talking about French fries, if you think about opening up the structure, how this is affecting the process efficiency. So by opening up the cells and going, for example, the heat penetrating easier into the product, it allows also to improve, to reduce, for example, the frying temperatures or also the frying time. So basically, all the process parameters can be reduced and optimized. This is resulting in a better color, for example, of the French fries. So you can see it in the picture. So the PAF-treated ones appears lighter, and they are also crispier. Another fact is what you can see here on the right side. The oil content is reduced. So 32% PAF-treated versus 35% untreated. It doesn't seem a lot of the reduction, but taking into account the huge amount of production, it's a lot of oil which can be saved. But if you going back to the color, this browning also brings us to another topic, which is the acrylamide. Acrylamide is formed at a high temperature basically from amino acids and reducing sugars. This is not really healthy, and everybody is looking to a method how to reduce the acrylamide content in different food products, like chips, for example. Vegetable chips are like from beetroot or carrot or sweet potato. They're very rich in the sugars, and that's why you also have very high acrylamide content. By PAF, so opening up the structure, you can easily wash out the reducing sugars and also reduce the frying time and frying temperature. So by this, it's possible to reduce the acrylamide content. And you can see, for example, for sweet potato, it's reduced by half. So it's a very huge reduction in acrylamide. All this reduction is good for the sustainability, of course. Having here an example of, for example, a 5 ton per hour raw potato chips production line, which produces around 5 tons per hour per year. So you can save about 1,736 tons per year on oil. And to compare this, it's an equivalent to around 178 football-sized rapeseed fields. So it's quite a huge oil saving. But as I mentioned earlier, you also have a saving in the yield. It's about almost 6 tons per year. And this is also here, nice equation here. It's equivalent to about 27 matches free, 25-gram chips for all supporters in the Camp Nou Stadium in Barcelona. So that shows that PAF saves a lot of oil, and it can increase the oil, so it increases the efficiency. Here's just a short summary what you can expect when using the PAF technology for potato and vegetable processing. What I just mentioned, so higher yield, a better and smoother cutting, reduced oil uptake, enhanced processing and expanded capacity and reduced costs, faster blanching time, improved texture control, new product opportunities, and an improved food quality. But this technology cannot only be used for these type of products. As I mentioned earlier, it's also affecting microorganisms. So basically, you can use this technology to inactivate microorganisms, and only the microorganisms, in liquid food products, for example, juices. So by this technology, you can increase the shelf life of these products while maintaining the high quality. Here on this slide, you can see some microbial data. So grape juice was previously inoculated with yeast, so Saccharomyces, and an E. coli. So and after PAF treatment at certain conditions, you can see that the microbial load was completely reduced down to the detection limit, resulting in an almost 5-log reduction from the yeast and 5-log reduction of the E. coli. As I mentioned earlier, this is also having an effect on the shelf life. You can see the total plate count of this grape juice. So after 15 days untreated juice, the total plate count is almost 10 to the 6 CFU per milliliter, so which means the juice is not good anymore and it shouldn't be consumed. And after PAF treatment, even after 61 days, it's still good because the total plate count is still low. And as it is affecting only the microorganisms, all the healthy stuff, so the vitamins and the components responsible for the flavor are maintained in the juice. So to sum up here, PAF allows inactivation of microorganisms at lower temperatures. You can expect a premium quality juice, improved extraction and increased yield. You have low running and maintenance costs. It's very to integrate it in a existing production line because it's continuously working. You can use any packaging material. And as I mentioned, it's a continuous processing. Another topic is biotechnology. This is also now very important for the research. A lot of research studies are focusing on this topic. One part of this is microalgae. Microalgae, you probably all know the famous one, spirulina. Spirulina contains the ingredient phycocyanin, which is giving this blue colorant of, for example, M&Ms. And to get out this phycocyanin, you have to break up the cells. Normally, it's done by different methods, mechanical or even by enzymes, but this is affecting the phycocyanin itself, but also the purity itself after the cell opening is very low. So PAF could here be a very gentle method to achieve the cell disruption. So you can see here on this microscopic pictures that after PAF treatment, you can still see the shape of the spirulina, this curved and curled cells here. So this shows that the cells itself are not destroyed. It's just pores are formed into the membrane so that important components can easily be extracted. And in this case, it's the phycocyanin. You can see here that a huge amount of concentration can be extracted, and also that the purity of this phycocyanin is very high. But this works not only for spirulina and microalgae in general, it's also working for yeast. So here's a microscopic pictures of yeast, control and after PAF. So we dyed it with methylene blue, which is going into the cell when it's open. You can see here that from the control one, there are just some which are blue, so which means most of the cells are closed and intact. While after PAF treatment, this colorant can go into the cell and can dye it. So they're completely blue cells. So basically, you can extract valuable components out of the cell, like oils, pigments, whatever it's in the cell. So, but it cannot not only be used for a cell opening, it could also be used as a stress inducer. So if you apply a very low amount of energy to the cells, they are stressed and they accelerate their growth. And also their metabolism is activated so that they start building different components inside their cell. So basically, using PAF for biotechnology, you can expect growth enhancement, a higher yield, in inactivation, of course, if you can go very high in energy, a fermentation control, and a stimulation. Another field which is very interesting for the PAF technology is the wine processing. You can see the general production of the wine. So first, starting with the destemming and crushing of the product. Here you can first add the PAF treatment to opening up this whole structure and to extract more, followed by a maceration, which can be reduced by PAF. Afterwards, a pressing, then fermentation. Then you can use a PAF again to accelerate this fermentation process, and afterwards it can be bottled. An example here, what you can expect when you use PAF for this wine application. So the cell structure is opened, and for red wine, for example, the extraction of polyphenols is very important because polyphenols are responsible for this deep red color and the intensive taste. So you can see here untreated and PAF-treated pictures of red wine, and after different incubation times. And you can see that the color intensity for after a PAF treatment is way higher compared to the untreated one. And this can be also seen here in the graphs. The color intensity after a PAF treatment is way higher, and the same also with the total phenol content, because this colorates. To sum up here, for the wine processing, you can expect an improved extraction, increased yield, enhanced quality. You are focusing on reduced maceration capacity, faster autolysis, and inactivation of microorganisms. As this is not only working for wine, you can also use it for the olive mesh. So by treating the olive mesh for olive oil processing, a higher yield can be achieved. And also what is way more important, the whole production is more gentle. So you can reduce the malaxation time and also temperature, so that you can expect a higher yield for the extra virgin olive oil, the EVOO, and enhance quality. Yeah, now it's about all the products. What about different PAF systems? So because all the products are different, so we are starting from potatoes like tubers and orange juice or different juice types, which has to be pumped through a pipe system. And also, what about trialing? And as I mentioned, biotechnology is strong currently used in the research. So there are different systems on the market. Basically, all the tubers and roots are treated in a belt system, and they can be treated also in industrial scale, already up to 60 tons per hour. Liquid products can be treated in a pipe system, or there are also smaller systems available which can be used for trialing purposes. Yeah, that was a short overview about the PAF technology. As I mentioned, it's a huge application area, and it was not possible to squeeze all the different areas into this presentations. So if you have any questions afterwards, I'm happy to answer.
Yeah, thank you also for keeping the time.
Yes.
I don't see questions yet, but please, dear audience, feel free to type your questions in the question and answer session so that we can take it up now or even later. In the meantime, you were referring to the equipment at the end, and you also mentioned all the different applications. From your point and experience, what is the most challenging when now implementing this technology in more or less very traditional processing environments? So talking about wine and olives and French fries production, these are all very set and established processes. So yes, yeah, what needs to be managed in order to make it a success when those new technologies and machines just arrive in, well, the old factories, let's say?
Yes, of course. First of all, they are all very impressed about what the technology can do. But then we have to face a lot of hurdles, because talking about wine, for example, it's a very seasonal process. So there, of course, the willingness to invest in a very, it's not very costly, but of course it's an investment. And so often these type of ROE, return of investment calculations, is not good enough for these old factories and often also small companies to come over. So it's very difficult for them to make the investment. Most of all, the systems are quite flexible, that they almost fit in each factory. So this is a hurdle which we already overcome. So I think this is done already. But just if we are facing new application areas, like, for example, treating leafy materials like spinach or kale, they are floating, and sometimes also they are cut in a process, so they attach to the walls. It's difficult to really achieve high throughputs there.
Okay, so it's more the
system-wise and of course also costing.
Yeah, okay, I see. So it's more the treatment chamber and the application of the electric field rather than its generation, right? So as I understood, the generators, they are pretty much there and can be connected to different types of processing environments and treatment chambers. Okay. Good, Claudia. Well, with this, still no questions, but if there's coming something into your mind, just write it down and we'll take it up later. Thank you very much, Claudia, for the field of electric fields.
I would like to invite Ugo Nicoletti for his talk on the application of radio frequency, actually, for heating processes of diverse food products. So Stalam is one of the pioneers and leaders in the drying and thermal processes in terms of radio frequency, with over almost 50 years of experience, I would say. But maybe Ugo will tell a little bit more about the company. Ugo is the sales manager of the Stalam, and so far I tried to find out it's more than 10 years with the Stalam. And Ugo, please can take over, and so to say, the screen is yours.
Thank you, Kemal. So my name is Ugo Nicoletti. I'm a sales manager of some application in the food industry of Stalam. Just to go quickly, Stalam is just a second. Okay, Stalam is an Italian company. We are based not so far from Venice, so in the northeastern part of Venice, of Italy. We have more than 40 years of experience in radio frequency, and we are focusing radio frequency machinery only that are used for drying and thermal processing application, not only in the food industry, but also in other fields. Just briefly, the radio frequency is a volumetric heating system. So practically, instead to bring the heat from outside to inside, with our machine, we can create the heat inside the product, like a microwave. Is quite similar. And the way that we generate the heat is very, very quick, so would say instantaneous. And so we can achieve a very quick and uniform heating of the product. We are focused in different business sectors, food, of course, but also textile, technical textile, and pharmaceutical. Briefly, I would like to explain how our radio frequency machine works. So normally all our machines are tunnels, or most of our machines are tunnels. So on the top of the tunnel, we have what we call generator that is able to convert the electrical power supply available in the factory of the customer, normally 380, 480 volts, 50 or 60 hertz, into an electromagnetic field that works with a specific frequency of 27.12 megahertz. And then this electromagnetic field is applied to the product inside the tunnel where there are two big electrodes. In between, we create a vertical and uniform electromagnetic field that release, let's say, the energy to the product in a very uniform way. So at the end, what we can do is to heat up a product very quickly and very uniformly. Here you see what happened to the molecular water that are inside the product when the product is surrounded, is inside an electromagnetic field. As the molecular water is a dipolar molecule, as we change the polarity between the electrodes that we have seen before, 27 million times per second, the molecular water will start to vibrate. This vibration will generate heat inside the product. So this is the mechanism. It's important to highlight that the frequency that we use, 27.12 megahertz, is an ISM frequency, so it is authorized, allowed all around the world for industrial, scientific, and medical application, and is a non-ionizing radiation, so it's not a dangerous radiation like the X-ray or gamma rays that could, change the DNA of the molecule. So we are far away from the ionizing radiation, so we can say that this frequency is absolutely safe for the operators and the humans. The main applications that we have in the food industry are, first of all, the defrosting. That is also the application that I'm directly responsible. So what we can do with our machines, radio frequency machine in the defrosting industry, is to heat up a product very quickly, normally from -18, -20 Celsius up to around -4 and -2 in a time that is between normally 10-30 minutes, depending on the product, dimensions, and characteristic. So as you can see, is a very quick process. But this is also not a complete defrosting, it's a tempering. So we always have to stop the process at a temperature below 0 in order to avoid that the product started to release liquid. This kind of technology is applied in the defrosting for many types of products, meat, fish, vegetables, and fruit. Later on, we will see some examples. The main advantages of the technology, of course, is that it's very fast, so 10-30 minutes. It's very uniform because when you defrost in a conventional way, so with air or water, normally you have the outer part of the product that is much more defrosted than the inner part. But when you use radio frequency, the differences are very, very limited. So we can say that the process that we offer to our customers is very, very uniform. It's a process, of course, that you can control with some parameters through which you can adjust the intensity of the electromagnetic field and the processing time. You can process the product inside the packaging, so you don't need to remove the packaging, and normally the packaging does not affect the processing time. The most important benefit is anyhow that you don't have any drip loss. So when you do the tempering till -4, -2, the product will not start to release any liquid. So you can save preserve the organoleptic characteristic of the product, and also you save the weight. So you can gain money, let's say. Is a continuous process, of course, so it's a tunnel, and you can take advantages of from the logistic point of view, and it's also a clean process, especially because when you treat the product inside the packaging, you cannot make dirty the machine or the floor, and so even from the sanitization point of view, is a very good process. Here are some examples of products that are processed with our machines. They can be naked in this case, so without any packaging, or they can be with packaging, carton, plastic film, or boxes. They can be blocks, so product frozen in block, or they can be IQF, so individual quick freezing frozen products. The meat can be lean or can be fat. Of course, fat products or products that with a different concentration that are not uniform, let's say, in the fat concentration, are more difficult to process, but are still feasible to process in the radio frequency. Now let's talk about another application, that is the post-baking drying. So normally we have the possibility to install a machine immediately after the baking oven in order to remove the let's say the last percentage of moisture from the product. Normally the last 3, 4, 5% of moisture. Here you see, for example, the main benefit when we install the radio frequency in after the baking oven. First of all, as we say, you can reduce the moisture of the biscuits or the crackers or sponge cake, and you can make it more uniform. As you can see from the graph, after the traditional baking oven, there is a moisture distribution that is not uniform across the conveyor belt. But after the RF machine, you can see that on the other side is very, very uniform. Another benefit is that as the radio frequency acts more where there is more water, you can see that with the radio frequency, you are able to really achieve a very uniform residual moisture content compared with an air dryer. The air dryer normally at the end of the process, you may have, for instance, biscuits with some spot with a higher concentration of humidity and other with a lower concentration that can then contribute to create the checking problem, so the product that will break easily after cooling. If you use the radio frequency, you can avoid this checking issue thanks to the greater uniformity of the residual moisture content. Another benefit is that you can increase the throughput of the line just even of, let's say, as you can see here, an example, from 500 kilogram up to 700 kilogram per hour, installing a radio frequency machines after the oven, and increasing the line of just a few meters. So this is another benefit that you can get. And of course, even before it was, we spoke about acrylamide. The acrylamide formation can be also reduced with the radio frequency because the drying process is down at a lower temperature. And so as you can see from the graph, you can reduce the acrylamide content even of 35% compared with a traditional oven. Some example of products that are treated with our machine are, for example, the crackers, the cereal bars, the cream puffs, cereal bars again, sorry, baby biscuits, and so on. Cookies, sponge cake. Okay, now let's talk about another application that we have, that is the possibility to pasteurize packaged products. like, for instance, this is just an example, bread, sliced bread. In order, of course, to increase the shelf life of the product. Here you see a typical line where you see at the on the right side the radio frequency oven and then some air chamber in order to keep the, let's say, the temperature for a certain time, for a certain period, the so-called holding time. As you can see, very quickly, we can increase the temperature of the product up to around 70-80 degrees, and then keeping the temperature for other minutes, we can get, you know, the proper bacterial reduction, and so the pasteurization. Normally, with this technology, we can reduce the pasteurization time up to 50%. So on the other side, we can increase the production capacity of 100%. Here you see, for example, in the case of bread, the cycle. So you see 10 minutes with a ref up to 70-80 Celsius, then 20 minutes of all time at 80 degrees, and you see how the molds and the yeast can be reduced. The same process can be applied not only to the bread, but also to the, let's say, pasta, packaged pasta, or cured meat also, for example. Another application that we can offer to our customer is the possibility to do disinfestation and sanitization of bulky product, like cereals, grains, or dry fruit commodities, and so on. Is a patented technology. Of course, again, one of the main benefits is that it's much faster compared with a traditional system. Is an organic and chemical-free process, and the physical and chemical sensorial property are, you know, preserved at best. Again, is a tunnel, so it's a you know, a continuous process, and you can have a low temperature drying for in order to preserve at best the characteristic of the product. Here you see an example of almonds, for example. Again, the process is very fast and effective. You can you know, very quickly to reduce the pest in case of, let's say, disinfestation. You can just reaching 55-65 degrees, you can reduce the you know, the pest in the products. We use this machine in different fields like nuts, cereals, legumes, mushrooms, and so on. And we also have application for liquid, so we can quickly pasteurize a liquid. Of course, in this case, we are not talking about a tunnel, but is a specific machine for liquid, so pumpable fluid. Again, the process is very fast and uniform. We can process product with particle inside, and the purpose is, again, to do a pasteurization, or sometimes also a sterilization process. The liquid can be with high or low viscosity. Of course, the processing time are different, but we can process more or less a wide variation of products. Here you see an example of product like strawberry, or that are used for the fruit preparation, for yogurt preparation, sorry, or apple dyes with syrup. Of course, we can also do a very fast pasteurization, so what we call flash pasteurization. We can increase the temperature of the product, of the liquid, even at a speed of 50-100 degrees per second when we are talking about a low viscosity liquid, or 1 or 2 degrees per second if we are talking about a high viscous liquid. Just briefly, I would like also to mention about the differences between a radio frequency and microwave machine. First of all, the frequency that we use is 27 megahertz. Microwave use 950 or 2450. Of course, higher is the frequency, lower is the penetration. So thanks to the radio frequency, we can have a much better penetration compared with radio frequency, compared with microwave. So especially in the defrosting, when we have to process blocks of meat with a thickness of 20-25 centimeters, this is never a problem for radio frequency, but could be an issue for microwave. And another difference is the way how the field is applied to the product. As you can see, in the radio frequency, we have a vertical and uniform field. In the microwave, we inject the wave from one point, and then the wave reflects inside the chamber, not allowing to get a uniform result in the product. So one of the main problems that you have with the microwave are the hot and cold spots. And then the amount of energy, let's say, that is absorbed by the product in the radio frequency machine depends on the product itself and on the mass of the product that is going through the tunnel, while on the contrary, the microwave is something that you have to adjust in the machine. Is one of the parameters that you set in the machine. So let's say that is more difficult to adjust a microwave machine than a radio frequency, as it is a self-adjusting technology. I finished the presentation, maybe it took too much time, sorry for that, but we have really several applications in our portfolio. Anyhow, if you need more details, here you can see my name for the defrosting or the names of my colleague for the other application. Pasteurization, grind, or of non-liquid or liquid products.
Thank you, Ugo. No worries for a few minutes talking longer. It's not a problem in this case. Thank you for a nice overview, and especially for comparing it to microwave. That would be my my question actually to talk. But we have a question in the chat which is related to the application of radio frequency to different packagings, and if there are any limitation using polyethylene, and in general, if there are, what are the limitations of packagings? Maybe you have some information if some packaging absorbing or reflecting more, or that's not an issue at all.
Normally, you know, especially in the meat or fish or vegetable or fruit industries, all the packages that are used are plastic that are, let's say, transparent to the radio frequency technology. So polyethylene is not a problem. Polypropylene is not a problem. Sometimes we have problem when, for example, in the carton, there are some labels or ink that are conductive. In that case, this is practically the only problem that we can have, but not related to the material, but related to the labels that are conductive.
So what would be solution then? Printing afterwards, perhaps?
The solution is or to take care or to change the type of ink, or to remove the carton from the product. These are the only solution.
The parallel to the microwave is quite interesting. Can you maybe quickly draw the parallel to the ohmic heating?
Actually, as I'm, mainly expert in defrosting, I don't have this technology of ohmic present in the defrosting. So honestly, I'm not able to do any comparison. But in the liquid, I know that the two technology are used for pasteurizing, as we can see from the presentation, but I don't know so much about the comparison. So if there is somebody interested to know more, I would suggest to contact my colleague Amatori, that is responsible for that. So he can explain better the differences and what could be the advantages or disadvantages compare. Yeah.
Sounds good.
Sorry for that.
Sounds good. Meanwhile, we have another question. Are there any limitations during drying if the level of water content decreases down close to the zero?
So if the level of water is close to zero?
Decreasing with the increasing water content, how low can you go? Or if that would possess or present any issues for the technology, for the drying?
I have my colleague here who is also expert in drying. So it depends. He told me from the product itself. Of course, we must say that the radio frequency add on the water. So higher is the water content, more energy the product can absorb. So practically, when at the end you don't have water, it's difficult to have absorption, and so it's difficult to remove the last percentage. Basically, I would say that by experience, when we do the drying of biscuit crackers, we can achieve a residual moisture content around 2%, right, Michele? 2%, yes. This is, I would say, the limit.
Thank you very much, Ugo. There are no further questions from the audience. If there's some popping up during the next few minutes, we can take them up then during the closing and the discussion.
Okay.
Thank you once again.
Thank you.
So the last but not least, it is up to me to present you a little bit on overview on the activities in the area of shockwave technology. I'm not sure if you can see my slides, to be honest. So I hope you can see my slides. Otherwise, just give me a sign. Perhaps
okay.
If
it's okay, Kemal.
that doesn't work. And yeah, as I mentioned, and it's stated in the agenda, I will try to give an overview also very briefly about the shockwave technology. Unlike the other three technologies that are rather advanced, let's say, in terms of their development and how far they are in the application area, most of them have over 100 machines already in operation. The shockwave technology is not that far away. I'm not sure that we have any application in the food industry for this type of technology, but nevertheless, it's a very dynamic technology and very dynamic development that are happening there. So what is basically the shockwave technology? Well, we can define it as the application of mechanical high hydrodynamic pressure or high energy pulses that take place in a fraction of a milliseconds, where we have a shockwave instantaneously generated basically at the core, and its reaching is maximum, and it's moved then along the time. So it's continuous. What is characteristic for a shockwave is that it propagates rapidly through the medium, which is in most of the cases water or similar media. it brings a high energy in the end, a high energy momentum, and if any objects are on the way, on the path of the shock wave, when pressure wave hits that object where this acoustic impedance differs from that of the water, kind of energy momentum energy and momentum transfer takes place, which in the end converts to a mechanical energy or mechanical stress that can tear up the structure and the properties of the product. In that sense, we talk about rather high local pressure. If you look at this graph, for example, or even at this graph, very local, but a very short pressure that then rapidly drops down in a very, very short period of time, as I mentioned, in a fraction of a microsecond. How shockwave can be generated when in some early steps of the generation, artificial generation of shockwave for different applications. The researchers looked into underwater detonation using explosives, and this is a form that can be applied, can be produced, but due to the technical and safety limitation, of course, reproducibility, the application of explosive, at least for a food application, was very fast, rapidly then abandoned in the 90s, where other forms of shockwave application and generation came into game by using electrical energy or conversion of electrical energy into mechanical. So in that sense, we can generate shockwave by using piezoelectric elements, something similar that we use in ultrasound, just at a higher intensity, or using electrothermal or electrodetonative approaches. The thing is, by moving from electromagnetic to electrodetonative, sure, we can increase the shockwave intensity, which is in several cases needed and required. But in the end, we have to keep in mind the equipment's integrity, the machine on itself, and eventually packaging or a product itself that it's to be treated. By looking at the scheme, for example, using an electrodischarging system, we usually have a charger system that charges the capacitors, basically for storing the electrical energy, in this case 36 of them, and then release this electrical energy to the treatment zone. And treatment zone is usually consisting of electrodes where the electrical discharge takes place between the electrodes. And when we apply this high voltage of 60 to 80 kilovolt per centimeter, then we are in the area where that field strength is higher than the electric strength of the water. Then we talk about the electric breakdown. In the beginning, we have a streamer between these two electrodes that basically defines the path of the discharge. And of course, due to the high voltage, due to the high electric field strengths, we have the ionization of the channel, basically where we have very high temperatures, and this plasma channel expands then immediately after the breakdown, and we have a plasma bubble that basically generates the shockwave and propagates then to the liquid. And due to this energy dissipation, we have this mechanical energy that is required for our destruction. When you look in the applications in the 80s, there was of course a non-food application. We were talking about extracorporeal shockwave therapy that was introduced as a quick and non-invasive treatment. First in the treatment of urinary stones, for example. Here we see a kind of a water bath where a person can lay down and then be treated very locally, but also other application that's related to allow for fracture healing and so on and so on. Other application includes selective separation of electronic waste or electrical devices, such as, for example, capacitor or general different kind of boards, motherboards, and so on, because we are attacking their mechanical weak points, and then in this way it's easier to separate them by using the shockwave. Talking about food, one of the major and the first application that was investigated in the 80s and 90s was how can we tenderize the food, or in this case, the meat, and if the meat tenderization can be improved in the sense of reducing the ripening and maturation time and improving the meat quality. So if you look at these microscopic images, for example, here we can see that untreated myofibril, for example, compared to the treated myofibril, where shockwave treatment was applied, then we have a kind of separation of myofibrils from the tissue. In a work that was performed at Bill some years ago, we did some studies where we also tried to identify these endomysium space, and if that increases, and if actually after the shockwave treatment, we have this kind of displacement of a muscle fiber, where the assumption was that there is an additional enzyme released into the tissue, which on one side we have a mechanical effect which helps tenderize the meat, but also we have other effects which are more of enzymatic and proteolytic nature that helps in the maturation of the beef meat. So by looking at this graph and comparing the cutting energy that is required for a control meat that it's unmatured, or let's say fresh meat, and compared to the conventional maturation, which typically takes 14 days for beef meat, and comparing the shockwave, we could basically half in the time for the maturation time by just using one shockwave pulse. And of course, we can reduce it a little bit, the tenderness, by using only shockwave, but of course, adding a few days of maturation time significantly improved the tenderness of meat. And there are many studies in terms of maturation and tenderness of meat, and major applications are still around that application, and interest of the industry goes in that direction. However, there are some other approaches from the early time. There were investigation if inactivation of microorganisms is something that could be achieved, and apparently there are some studies it is possible, but in the end I think there are more efficient ways and other ways how to do this treatment. Other than microbial inactivation, we have also changes or improvement of functionality has been reported in Frankfurt sausages, but also in the general, similar to the path where we have the disintegration of the tissue, be it for purposes of extraction of juice or valuable compounds. The shockwave is technology that can be used for. It's just a matter of applicability and how really beneficial that is if we have already path technology at the spot that it's already developed, and in particular for this purpose. However, some applications where PEF may be not be necessarily working is general mechanical disruption of the tissues, of the harder tissues, like in the case of the seafood, or opening and crushing the nuts and so on. And this is the area where current research is ongoing from the potential application side, and how can we convert this electrical energy into bringing more into mechanical disruption of the tissues that are to open in that sense, improving also maybe a footprint, in particular when we think about seafood that is often transported to another continent for peeling, and then it's transported back for consumption. And if we can do everything at one place, of course, with the of certain economic and environmental benefits. Of course, when we talk about meat standardization, there are options to do this inside of the packaging and outside of the packaging. The challenge is the packaging stability, because as we've seen tracking the walnuts, it's not a big problem because there is also air pockets inside. But sometimes also there are air pockets in the packaging, in different packaging, and also in the meat packaging in between, which then in the end can result in serious damages of the packaging, which then should be kept in mind, and maybe also do some further developments. There are certain bags and certain materials that are better resistant to shockwave treatment than the others. And these are usually used, but in the end, we want to move away from using packaging in this type of treatment, but rather using the direct contact of meats and the shockwave in the concept that I will show you a bit later on. From the machine perspective, as I mentioned, we have usually a power supply and a capacitors that store the energy and release it using the switching system underwater. This can be done without a wire, where we simply have two electrodes, and the electrical connection or electrical discharge takes place between the electrodes. Or we are using an exploding wire. This helps basically to significantly improve the conversion rates of electrical energy to acoustic, but it's rather challenging in terms of reproducibility. This can be done on a batch system where the wire basically evaporates due to the high energy, and due to the expansion evaporation releases basically huge amounts of energy. In sense of new developments, this one's developed and installed at the CSIRO in Australia for the purposes of for the research and demonstration purposes, mostly in the area of meat. Here you can see again the configuration of the electrodes where the electrical discharge takes place. What we try to develop now is a kind of a different form of a vessel, where we have electrodes within the treatment chamber, and where eventually a membrane can be placed on the top, so that the membrane is then in direct contact with the meat product, for example, or to introduce another vessel in between to either reduce the volume or to concentrate the energy of the shockwave, and for a different application, mostly in the research phase so far. So here you can see the one large cylinder, and then we have the electrodes inside, and then this reduced volume cylinder, so to say, where then the water is, for example, put in place, and then we have a membrane that is closed, and then the product can be filled in here, for example, shrimps and so on, and then closed, so that we have a direct treatment through the membrane and not direct contact with the water. So a bit of an update on the research activities. Of course, we are testing different points, different measurements, diameter of vessel, varying the voltage, and so on and so on. And using then high pressure sensitive paper to basically evaluate the distribution of the pressure, the intensity of the pressure, and how that can be utilized for further applications, for example. And here's just one slide on the results that we obtained. For example, how does it relate the distance from the shockwave origin, how the intensity changes, and so on and so on. And the distance between the electrodes is a shockwave then of a high intensity if the distance between the electrodes is larger or shorter, And then what kind of media do we use in terms of electrical conductivity, for example, but also density of the media, what kind of membrane. And yeah, these are the aspects that we are focusing research at this point. As I mentioned, the technology is not at the stage to be taken up by the industry and with a certain application. However, the most promising application being meat standardization or improving the ripening time or mechanical disruption of hard-shelled food products. And with that, that brings me to the end of the talk, and I'm curious if there will be any questions from the audience. So far, there are no questions from the audience. That brings us then to the last step of the webinar, which is basically conclusion and discussion. So, Henry, I hand the word again to you for the final words, and if there are some questions again to be addressed.
Thank you, Kemal. Yeah, I think with the 4 presentations, it nicely illustrated what potential the new technologies bring, what different basic principles of processing we are using, just thinking about the electroporation, for example, and how this can be applied in food processing. However, we also saw that one of the main challenges is equipment availability. So the food industry basically needs robust equipment. And this is what in the past years, for example, for the pulse electric field technology, but also now for the ohmic heating technology, needs to take place and needs to be continued in order to convince the food industry in order to really take those benefits that could be derived from the new processing technologies. And still, what we also learned, of course, since we are operating with different principles, some of the variables are not very familiar to the food industry, and this is probably also one reason why there is a certain delay in taking up those technologies. Yeah, looking at the audience again, no additional questions so far. I think all our contact details are available via the EFCE website. Also in the presentations, they were included. So please feel free to reach out to us. Also with regard to suggestions or needs for further webinars. So if you have any topics related to food process engineering, food technology, please feel free to get in contact to the food section. And we are very happy to take up your needs in terms of training, education, knowledge exchange. All this is what the webinars are for. So please get in contact and help us to expand our network in food process engineering. Yeah, with this, I thank you once again for taking part, and for the final words, as we started with Giorgio, I let it to you to also conclude from the EFCE side. Thank you.
Yes, thank you, Ari and Kemal. I think, and to all the speakers, I think it was a very, very interesting, at least for me. I'm not an expert about food, so I think that this webinar was very much inspiring, and I think I'm very curious to know more about these technologies now that I've learned so many things you can achieve with these technologies. And of course, because of my background, I'm more used to thermal applications, so very interesting. I have a couple of observations. Maybe you can answer directly, as we have a little bit of time. The fact that we have participants, speakers coming from Germany and Austria and northern Italy. Do you have any? Is just a chance, or maybe most of the let's say research and the manufacturing capabilities are in these countries?
Well, with regard to research, I think also the network is larger, but since we were limited to 4 presentations, we had to pick some, and we wanted to make a good match between industry and also some research. But of course, looking into pulse electric fields, we have a strong research community in France, in Spain. So this is clearly there. With ohmic heating, I mean, Felix showed some examples here. Italy is quite strong with regard to equipment manufacturing, but also potential applications. And yeah, for the others, I mean, with the shockwave, I think the DIL is quite the leading party in this. With the microwave and radio frequency heating, Kemal mentioned that Stalam is also one of the pioneers. So I think this was more or less the reason why we selected the speakers. But certainly there are some research activities also going on around Europe and also overseas. The colleagues from the US are quite strong in non-thermal food processing, basic mechanisms, microbial inactivation. So also here there is a community quite active in this field.
Okay, thank you. And the second thing, I'm happy that, you know, it's very well spread. The other point I wanted to raise is to solicit people who have listened to this webinar and are not members yet of the section, you know, that they can apply to become part of the section, active member of the sections through the member society or directly through application to the chairs and co-chairs. So I think that, you know, it's very useful to be part of a community, to exchange ideas and to have, you know, share experiences. So I really encourage that to do because it's very effective way to work.
Yeah,
So,
and also related, if I just may interrupt, to our PhD workshop, the European PhD workshop. Also here, we have a long email list of colleagues and research groups active in that field. But also we are very happy to learn about new groups that would like to participate and nominate PhD students that are active in the field of food processing and food technology. So yeah, please feel free to get in touch.
yeah, okay. So I think we can close it here. I would like to thank you again, Henry and Kemal and all the speakers about your presentations, about your effort, preparation. And as this is the last webinar of Spotlight Talk of this series, I would like to thank all the people that have participated. And again, Martin for a hard work for this and for all the others. Thank you very much, and
Thank you.
see you soon at the next occasion.
Thank you.
Thank you
Look
also from
forward.
my side.